Here's my video lab report on Lab 2 motion of a falling object. In this video lab, I will introduce the key objectives and key equations I will be using within this lab. I will then show my video within the tracker software, show the data I collected with drag and no drag, and the mathematical calculations computed. I will then show my GlowScript code and finally close with discussion questions and a conclusion. The purpose of this lab was to observe the motion of an object falling and examine the drag force and its impact, as well as construct a computational model in GlowScript and compare the observed data in Tracker to the computational models of gravity and drag. Some key equations that will be used are Newton's second law, which force equals mass times acceleration, being divided into F net divided by mass, and finally written as the final velocity equals initial velocity plus the net force divided by the mass times change in time. When an object falls to the ground, the velocity of the object is not constant. Since the velocity is not constant, we know drag force is a constant that is opposite to any object in motion. This can be calculated by using the equation b times velocity squared, where b is a proportional constant that depends on the properties of the object. Next, I will explore terminal velocity, where the velocity of an object is no longer changing, or when a certain velocity is reached. This is calculated when drag force is equal to the force of gravity. Here is my video of me dropping my EOS lip balm within the Tracker software. In Tracker, I plotted the point of mass for each frame, resulting in getting the data for me to compare to the conceptual model. Here is just the data collected: the mass of the lip balm, the radius, the start and end times, the time step, the initial position, the weight force, turbulent drag or B, drag force, and net force. In the next slide, I will show how I implemented this data into the GlowScript code in order to get a graph. Here's the code for the no drag model. As seen here, everything that is highlighted is very essential into graphing this model. Here we have the mass of the lip balm being 0.007 and delta t, or the time step, being 0.033. But what's very important to this experiment is that the acceleration equals gravity, in this case where g is 9.8, and that j hat is 0, 1, 0, as we only care for the y direction. These two factors alone with the mass of the lip balm are essential to computate the weight force. Since we're computing for no drag, b, the proportional constant, is not intended or not used to find the net force. From this, I set the net force equal to the weight force, and then use the position and velocity update equations to get the motion of the lip balm. Here is the graph of the observed versus no drag computational model. As you can see here, the purple is the no drag and the orange is the observed. But in the beginning, they tend to be together. Towards the end, they start to spread out. They spread out because we know there must be some force acting upon. Here's my GlowScript code incorporating dragged. Mostly everything remains the same from the previous two slides, but B is incorporated and the net force is now changed. In my case, B is equal to 0.002. This was calculated by guesstimating how close I could get B to equal the final position in my observed model. After doing this, I updated the net force to being FD plus W. Since we're accounting for drag, in this case, W is the weight force in the negative position, while drag is in the positive direction. Here's my observed model compared to the computational model with drag. In this case, you can see that the lines are closer together and are curved at the beginning, but begin to follow this constant linear shape towards the end of the line. This means the lip balm has reached terminal velocity, and this will be addressed in the next slide. Here is a final graph displaying drag, no drag, and observed data. As stated before, the object does reach terminal velocity due to the drag force being equal to the weight force, causing zero acceleration. The EO starts at 0, but as velocity increases, the drag force increases as well, causing them to equal each other, resulting in zero net acceleration. Let's say if the EOS lip balm was initially thrown, would terminal velocity still be reached? In this case, yes. If given a non-zero starting velocity, Terminal velocity would just be reached faster, but it would still stay the same. In conclusion, it's evident that drag force influenced my object in this lab. Also, this lab shows the importance of accounting for all forces when attempting to determine the net force. Thank you for looking at my lab report for Lab 2, Motion of a Falling Object.